Why are supercritical CO2 cycles key for heat engines? Imagine a power plant that is smaller, more efficient, and better for the environment. That's what supercritical carbon dioxide cycles can do for heat engines. These cycles use carbon dioxide in a state called supercritical, which means it is hotter and pressurized beyond its critical point. When CO2 is in this state, it acts like a mix of liquid and gas, giving it special properties. This unique behavior helps heat engines work better. In traditional power systems, steam is used as the working fluid. Steam goes through boiling and condensing, which makes designing heat exchangers more complicated. It also limits the maximum temperature because of the boiling process. Supercritical carbon dioxide avoids these issues because it stays in a single phase, no matter how hot or pressurized it gets. This makes heat transfer easier and more efficient. Because supercritical CO2 is denser than regular gases, it takes less work to compress it. When you compress a fluid, you need energy. Since less energy is needed with supercritical CO2, the whole cycle becomes more efficient. In fact, these cycles can be about 10% more efficient than traditional steam cycles under similar conditions. That means more power from the same heat source. Another big advantage is size. The equipment needed for supercritical carbon dioxide cycles can be much smaller. Turbines and heat exchangers can be about 1/10 the size of those used in steam plants. Smaller equipment costs less to build and takes up less space. This makes power plants more affordable and easier to install, especially in places where space is limited. From a mechanical point of view, turbines that run on supercritical CO2 are simpler. Unlike steam turbines that need multiple stages and complex casings, supercritical CO2 turbines can be designed with fewer parts. This reduces maintenance and makes the system more reliable. Plus, supercritical carbon dioxide is safe to use because it is not toxic or flammable. It also handles high temperatures well, so it can work with different heat sources like fossil fuels, nuclear reactors, solar power, or waste heat recovery systems. All these factors make supercritical carbon dioxide cycles very appealing. They boost efficiency, cut costs, simplify design, and are flexible with heat sources. That's why they are considered a key technology for future power generation and industrial processes.